All right, let's get into Chapter 6, Discrete Probability Distributions. So this is Professor Thomas's statistics lecture video, and we are only going to focus on the first two sections of Chapter 6. All right, so the first section is dealing with discrete random variables, and there are a lot of different learning objectives. All right, you're going to distinguish between discrete and continuous random variables. And it's pretty consistent with what a discrete and continuous numbers were. Identify discrete probability distributions, graph discrete probability distributions, compute and interpret the mean of a discrete random variable. Interpret the mean of a discrete random as an expected value, and compute the standard deviation of a discrete random variable. Distinguish between discrete and continuous random variables. So here we give the definition of a random variable in the first place. So, is a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as X. And notice that's a capital letter X. A discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line with space between each point. So basically they're the whole numbers. A continuous random variable has infinitely many values. The values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So continuous number line where between any two numbers there's another number. We call it a continuum of numbers. So we have fractions, decimals, all sorts of decimals in between every number. We're not just talking about the whole numbers. Distinguishing between discrete and continuous variables. So here we have a problem for part A. It says the number of A's earned in a section of statistics with 15 students enrolled is a discrete random variable because its value results from counting. If the random variable X represents the numbers of A's, then the possible values of X are 0, 1, 2, so on and so forth, all the way up to 15. The number of cars that travel through a McDonald's drive-thru in the next hour is a discrete random variable because its values results from counting. If the random variable X represents the number of cars, the possible values of X are the speed of the next car that passes a state trooper is a continuous random variable because speed is measured. If the random variable S represents the speed, the possible values of S are all positive real numbers. So it's some S greater than 0. Notice how they said that the speed is measured instead of counted. That is a huge distinction between discrete and continuous, all right, whether or not we're counting or we're measuring. All right, so objective 2 is to identify discrete probability distributions. So the probability distribution of a discrete random variable X provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, graph, or mathematical formula. Suppose we ask a basketball player to shoot 3 free throws. Let the random variable X represent the number of shots made, so X could be 0, 1, 2, or 3. Table 1 shows a probability distribution for the random variable X. So this is a probability distribution table here, and we have probability distribution for this random variable, and it looks like all of them will add up to 100. Probability is 100. All right, we denote probabilities using the notation P of x, where x is a specific value of the random variable. We read P of x as the probability that the random variable x equals x. All right, so for example, the probability that the random variable x equals 3 is 0.51, and that is what we have in the chart. So there's a really good chance that the basketball player will make 3 of the 3 shots. So here's some rules for a discrete probability distribution. So if we let P of x denote the probability that the random variable x equals x, then the summation of all those probabilities of x should be 1, and also the probabilities of x should be between 0 and 1, inclusive. Which of the following is a discrete probability distribution? Well, we could reject this one, all right? The random variable of 5 has a negative probability, and that just goes against one of the rules requirements. Here's another one, but wait, do they all add up to one whole? And they do not. You can check the ones column. We have a 9 and another 9. That's 18. That's not going to total it. All right, what about C? Well, this looks really good. We have 10, 50, 60. Yep, that's good. So C does equal a discrete probability distribution. All right. What about the graphs of discrete probability distributions? Let's take a look at some graphs. So here it is. It's plotted out, the graph of that distribution. So here it says compute and interpret the mean of a discrete random variable. All right, so the mean of a discrete random variable is given by this formula. All right, so it is the summation of the discrete variable times its probability, and you add them all up, and that's the mean. So where x is the value of the random variable and px is the probability of observing the value x. So here it says compute the mean of the discrete random variable given in table 1 used previously. So the first two columns represent the discrete probability. The third column represents the product of each one. And now what we have to do is sum up that last column. And when we sum up that last column, it looks like the mean is 2.4. So that would be the mean, the average amount of shots that we could expect. Obviously, making free throws is a discrete countable number, so this mean doesn't make much sense, but it can be interpreted to mean that you have a good chance to make on average 2, maybe 3. So again, suppose an experiment is repeated n independent times and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean value of the n trials will approach the true mean, the mean of the random variable x. So in other words, let x1 be the value of the random variable x after the first experiment, and x2 be the value of the random variable x after the second experiment, so on and so forth. So eventually, if we were to take the average of all of those means, it will give us the real mean. So the difference between the mean and mu gets closer to 0 as n increases. So the basketball player from an earlier example is asked to shoot 3 free throws 100 times. Compute the mean number of free throws made. All right. Well, obviously, um, you know, 100 times is quite a lot. So sometimes what we can do is run a simulation to simulate this event. Now the data looks like we have it out. I mean, that's 10 by 10. So there's the first experiment, second, third, and so on and so forth, all the way down to the 100th. So in the 100th time he did it, he got all 3 shots. At one point he didn't get any shots. That only happened once out of 100 times. So we actually have to compute the mean here. So what we would do in the first experiment, so on and so forth. So we do it, we divide by 100, and we get that the mean number of free throws made was 2.35. This is close to the theoretical mean of 2.4. As the number of repetitions of the experiment increases, we expect x to get even closer to 2.4. Figure A shows the mean number of free throws made versus the number of repetitions of the experiment for the data in Table 4. Figure B shows the same information when the experiment of shooting 3 free throws is conducted a second time for 100 repetitions. And here it is, it's plotted out where we have the number of repetitions and on the horizontal axes, and we have the means of each one. Notice that it will approach that theoretical mean of 2.4. And that has, again, that does have to do with the law of large numbers as well. So compute and interpret the mean of a discrete random variable. So because the mean of a random variable represents what we would expect to happen in the long run, it is also called the expected value, E of x, of the random variable. So here we have a problem, and it says finding the expected value. So a term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. So these policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, the probability that the male will survive the year is 0.998937. Compute the expected value of this policy to the insurance company. All right. Well, here, if x survives as 350, here's the probability. If x dies, we have the probability here. So to actually compute the expected probability, we have we take the product and we summate them, and we get $84.25. So the company expects to make $84.25 for each 18-year-old male client it insures. The $84.25 profit of the insurance company is a long-term result. It does not make $84.25 on each 18-year-old male it insures, but rather the average profit per 18-year-old male insured. Because this is a long-term result, the insurance idea will not work with only a few insured. So now we're going to talk about computing the standard deviation of a discrete random variable. keep in mind, we have technology to do this. The standard deviation of a discrete random variable x is given by this. X is the value of the random variable, and mu x is the mean of the random variable, and p of x is the probability of observing a value of the random variable. So we have two different formulas, and these are equivalent. So here it says find the standard deviation of the discrete random variable. Alright, so we'll use formula 2a with the unrounded mean. And then we're going to subtract the mean from each one, square it, and then multiply by the probabilities, and then add it all up. And when we do that successfully, we get 0.4979, and then we'll simply take the square root of that number. And we get 0.7. All right. Here's the other formula. So here it looks like we're squaring each discrete random variable, multiplying it by the probability, and then we take the sum of all of that, subtract that from that mean squared, and again we get the square root of that number. It's again approximately 0.7. Now here it says using the statistical software or a graphing calculator to find the mean and the standard deviation of a random variable whose distribution is given in table 1. And they did it. I guess it probably would be a good idea to try to do this as well, just so that we're clear on how it's done. They didn't show the data entry part of this, so I'm going to go back to table 1 and let's just take a look at how we would enter this in. So right now I have two lists. We have the random variables and then the probability. So in stat and edit, I'm going to, first of all, I need to clear all my lists. So let's go back to stat. Let's choose 4, clear list. And we're going to clear list 1, comma list 2, comma list 3. And let's do list 4. Done. So now what I'm going to do is go back to stat, edit, and I'm going to enter my data in. The first thing I'm going to do is enter this on 0, 1, 2, 3. And then in the next column, I will enter 0.01, 0.10, 0.38, 0.51. All right. So the data is in. Let's take a look at the data one more time. We got 0, 1, 2, 3, 0.01, 0.10. So now the question is, well, how do we actually get the mean and the standard deviation? So what they did is they go in the stat, and then calc, and then one var stats. So we have list 1, and we also have a frequency list. We'll call it list 2. Hit calc. And now you see we have it. We have the deviation as 0.70, and the mean was 2.39. So that's for how you would calculate it using the Texas instrument. Okay, let's move on. Finally, we're going to get to 6.2, the binomial probability distribution. All right, and we have 4 different learning objectives here. determine whether a probability experiment is a binomial experiment, compute probabilities of binomial experiments, compute the mean and standard deviation of a binomial random variable, graph a binomial probability distribution, and that's the 4 objectives for section 6.2. So let's take a look at the very first one here. So it says a binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are 2 mutually exclusive outcomes. These 2 outcomes are generally referred to as a success and failure. Okay, so such as making a free throw or missing a free throw. Experiments in which there are only 2 outcomes are possible are referred to as a binomial experiment, provided that certain criteria are met. Criteria for a binomial probability experiment. An experiment is said to be a binomial experiment if, here we go, the criteria is, number 1, the experiment is performed a fixed number of times, so each repetition of the experiment is called a trial. The trials are independent. This means that the outcome of one trial will not affect the outcome of the other trial. For each trial, there are only 2 mutually exclusive outcomes, success or failure. The probability of success is fixed for each trial of the experiment. Let the random variable x be the number of successes in n trials of a binomial experiment. Then x is called a binomial random variable. So here's some notation that's used when we're referring to a binomial probability distribution. There are n independent trials. Let p denote the probability of success for each trial, so that 1 minus p will be the probability of failure. And then finally, let x denote the number of successes in n independent trials of the experiment. So we have 0 is less than or equal to x, which is less than or equal to n. And the first step is to determine whether something is a binomial experiment. So for those that are binomial experiments, identify the number of trials, the probability of success, the probability of failure, and possible values of the random variable x. An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. So the probability of success would be 80%. This is a binomial experiment because there are n trials, and each trial is independent of each other, and there are 2 possible outcomes. The probability of success is 0.8, and the probability of failure is 0.2. The probabilities are the same for each trial. The random variable x is the number of free throws made, with x equals 0, 1, 2, or 3. According to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained, and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. This is a binomial experiment. There are 10 trials. The trials are independent. There are 2 possible outcomes. You either like chocolate or you do not, and the probability of success is 0.28, and the probability of failure is 0.72. The random variable x is the number of people who chose chocolate as their favorite ice cream. Here's another example here. We have a probability experiment in which 3 cards are drawn from a deck without replacement, and the number of aces is recorded. Alright, so this is not a binomial experiment. The trials are not independent. The probability of an ace on the first trial is 4 out of 52, and because we're sampling without replacement, if an ace is selected on the first trial, the probability of an ace on the second trial is different. It's 3 out of 51. If an ace is not selected on the first trial, the probability of an ace on the second trial is 0.078. Alright, note that the word success does not necessarily imply something positive. Success means that an outcome has occurred that corresponds with P, the probability of success. So now we're going to compute probabilities of binomial experiments. So according to the Red Cross, 7% of people in the US have blood type O negative. An SRS of size 4 is obtained, and the number of people X with blood type O negative is recorded. Construct a probability distribution for the random variable X. So we're going to construct a tree diagram. Now compute the probability of each possible value of the random variable. Yeah. The successes and failures, so on and so forth. We're multiplying them up because they're independent events. Here we present the results in the probability distribution table. So they actually calculated all of the different probabilities and they've listed it out in a table now. Here is the binomial probability distribution function. This is that formula. And we do use our technology to compute probability distribution problems. When reading probability problems, pay special attention to key phrases that translate into mathematical symbols. The table 9 lists various phrases and their corresponding mathematical equivalent. So if they say at least, or no less than, or greater than, that's greater than or equal to. More than, or fewer than, is greater than, less than. No more than. And then when they say exactly equals, we have exactly equals. This is a nice little chart. So here is our problem here. It says according to the CTIA, 72% of adult Americans would rather give up chocolate than their cell phone. A random sample of 10 adult Americans, what is the probability that exactly 8 would rather give up chocolate? Well, we're going to use that formula. And the formula here is probability of 8. We're dealing with a binomial distribution problem. Yeah, and what they're doing is they're plugging all these values into your formula. We don't have to calculate it this way. This combinatoric function is found in math. If you were to click math and go all the way over to PROB, you would get that. But we're actually not going to use that. Okay? What we're going to do instead, let me bring back up that calculator. I'm going to demonstrate how you would find this using the binomial function in our calculator. So we're actually going to go over to distribute, and we're going to go all the way down to binomial CDF. Well, there's actually two. There's binomial CDF and binomial PDF. Now, CDF is when we're dealing with at least or at most. That's when it's a greater than or equal to type of problem. We're dealing with the exact. They said find the exact amount. And so that is an A. We're going to go into A. And then we have to list the number of trials. The number of trials is 8. I mean, the number of trials is actually 10. And then the probability of success is 0.72. And then the X value, which is the exact amount, is 8. And now we're going to put this, we're going to paste this onto the home screen. So it's binomial PDF 10, 0.72, 8. So it's the trials, the probability, and the x value. So we got 0.2548, and that's pretty much what they got when you round it off to 4 decimal places. Okay, 0.2548, that's what we got. We got the exact same thing, and that's how we do it. Okay, we use our technology to do it. I'm sure StatCrunch and other softwares can calculate it. Even Googling binomial calculator will be able to calculate this for you as well. So now we have to be able to interpret what we got. Like, what does it actually mean? So the probability of getting exactly 8 adults out of 10 who'd rather give up chocolate is like 25%. So out of like 100, we'd expect about 25 people. Out of groups of 10, 8 of them exactly would prefer to do that. They would give up chocolate than their cell phone. All right, so the other question is fewer than 3. So that really means 2, 1, or 0. So that's the phrase fewer than 3. The phrase fewer than 3, we can write it as the probability of x is strictly less than 3. So we're really dealing with the probability of 0 or 1 or 2. So you'd find the exact values there, those 3, add them up. That is a lot of work. Thankfully, we can do this problem in 2 ways. We could add the 3 of them up. I mean, what if okay, it's like, for example, what if I did 0 plus, wait, no, why did, okay, uh, plus, plus, and what I'm going to do is change those values. I'm going to put 0, 1, and 2. And let's do 2. All right. Well, we got a number so small that they put it in scientific notation for us. We got 1, 2, 3, 4, 5, 6. That's what we got. And you can put that in scientific notation. It would look like this. Um, let's see. Does that actually match what we got here? It looks a little different, believe it or not. Um, what we could do though is use binomial CDF. Because maybe something didn't work out too good here. So what we could do is use that, and let's do that instead. Let's go into distribute, second distribute, and go all the way down to binomial, this time CDF. So we're going to use CDF. The first time we used PDF, that's when it's the exact value. But this time we're going with 2 and less. So that's a cumulative. So we can use at this time the trials were 10. The probability of success is 0.72. And then finally the x value was 2 and lower, fewer than 3. And this is what we get. Okay, so when I did mine's, maybe, let's see here, maybe I didn't enter something incorrectly by mistake. We got a different value. But it matches the exact value of what they got. Okay, so when you put in the binomial CDF, it gives you the cumulative from 2 all the way down to 0, and it adds it up for you. So that is the same as 0.00096. It's the same value. Oh yeah, we didn't add it. We missed the plus symbol. Yeah, we gotta insert a plus symbol, and then we would have been okay. All right, yeah, it works. Let's move on. This time they're saying at least 3. So at least 3 would be 3 all the way up to 10, and this is how you would do it. This would be extremely tedious to do, but it's actually the complement of at most or fewer than 3. So we can actually just subtract our 1 from our last answer. We can subtract our last answer from 1 to get the right answer. So that's pretty slick. And it also works because all of them added up will total 1 whole. So if the bottom 3 is 0.009, from 4 all the way up should be the rest. So we subtract it up. The total must add up to 1 whole. Okay, and what about the case where the number of adult Americans who would rather give up chocolate is between 5 and 7 inclusive? So basically we're talking 5, 6, and 7. So you just do the exact amounts and add up all 3. Here's some more problems here. Now it turns out that you can actually calculate probability using a table as well. If you did not have a calculator, or if your calculator failed you, you can use a table, and the table will give some probabilities for you. Here it is. When n is 15 and x is 10, and the probability is 0.65 of success is 0.65, the actual probability of exactly 10 would be 0.2123. No more than 6. So that's 6 and down. Okay, we're actually including 6. So you would do 6 and down, and then add up the rest. They do demonstrate how you would do this using your calculator for the cumulative distribution function. That's going from 6 and down. Alright, we're going to look at how you would use the mean and the standard deviation. Take a look at that formula there. So we got mu of x is equal to np, and the standard deviation is the square root of np times 1 minus p. And remember, 1 minus p is the complement of p. So there we have the mean and the standard deviation. So here we calculate the mean to be 0.72 times 300 is 216. We would calculate the standard deviation as 7.8. We can also graph the binomial distributions. There we go. We can see if they're skewed or not. So if we check the mean and two deviations away from the mean from the left and the right, we would expect about 200 to 231. This lets us know about 95% of all the values will be in this range. Around 95% of all the values are within two deviations of the mean. Alright, we're going to take a look at some of the practice problems for Chapter 6. Alright, so it looks like we have about 21 different questions, and we'll just click on a couple and get a feel for the kind of questions that we're going to have to do. What is a random variable? Alright, now we gave this definition. It's pretty straightforward. You can also check your notes for that one. That would be pretty easy. Alright, let's move on. What are the choices anyway? A random variable. A random variable is a numerical measure having either a finite or countable number of values of the outcome of a probability experiment. A random variable is a numerical measure of the outcome of a probability experiment. Or a random variable is a numerical measure having values that can be plotted on a line in an uninterrupted fashion of the outcome. I actually like B, and the other two are good too, but that's more specific when we're talking about a discrete random variable or a continuous random variable. But in terms of just a plain old random variable, there it is. So let's kind of go through this. What are the two requirements for a probability distribution? As we said, the probabilities must be between 0 and 1, and the sum of all of them should total one whole. Not too bad. Is this a discrete probability distribution? It's a good question. This is because boom, boom, boom. Okay, so you'll fill that out. Good. Not bad. All right, now They actually want us to create the probabilities based on the data that we have here. And this shouldn't be too terribly difficult. The probability of X happening would be 17 out of the total. So it's just a matter of adding them all up. If we add the ones, that's a 7, 8, 9, and then 16. And if we add the tens, that's 30, 50, 80. And 80 and 16 is 96. So 17 out of 96, which turns out to be, I got 0.771. Let's see if that's good. 1771. Well, I would have to complete the rest of these. Let's see. 0.2188, and that's also 2188. And then we're going to subtract the last one from 1. This one's the most, so I got 0.3854. And again, we're using the frequencies. Let's make sure that is right. It worked out for us. We're using the frequencies divided by the total number of attempts altogether. And now at this point you will plot based on the table where the P of X is on the horizontal, or actually the vertical axes there. So you look at what scale would make the most sense. I mean, if it's 0.5 and we're going 1, 2, 3, 4, so everyone's a 0.1, 0.2, 0.3, 0.4, 0.5. So you'd kind of just go through and eyeball it and see which one makes the most sense. 5 and 6 should have the same probability. So you want to look for one where they have the same. Alright, let's take a look at some of the ones in the very bottom. So here they're asking for compute the theoretical mean. And here we have the table of the number of hits for 25 games, the table of the number of hits for 50 games. So we have a lot of different data, and it says compute the theoretical mean of the random variable x for the given probability rounded 3 places. Well, if this is our table, then what we can do is use our technology to actually solve this problem. We did a problem similar to it. In one list you would put 0 through 5, in the other list you'd put the probabilities. You would do one var stats with a frequency list, and then you will actually get the mean. So that seems pretty straightforward. I don't know what else they really want you to do there. Okay, this is straightforward. You're just working with bigger numbers at this point. Compute the mean, and they might even ask for the deviation, right? Not too bad. The mean square footage would be what? So they want us to approximate. We would probably have to use a number that's in between 0 and 499. and then multiply that by 9. So what we could do is use an approximation for each one of these classes and then put that in the list. And then the second list will be this frequency list. And then we would get the mean. Pretty straightforward, okay. Not too bad. Alright, they want us to construct the frequencies based on this, okay. Just tally them up, record the numbers that you see of each tally. One of the biggest factors in determining the value of a home is the square footage. The company data represents the square footage and asking price for a random sample of homes for sale. Click the icon to view the data table. So we have paired data with the X and the Y, and it says which variable is the explanatory. Well, that's the X. The X is the explanatory. So we would go with square footage. And then draw a scatter diagram. Well, that's just a matter of, well, we probably can open this. Well no, that's there. This is the critical values. The data's here. We probably can open this in StatCrunch and then quickly get the data. We will say that's that and that's that. What else do I need? I think I'm good. I think we can just hit compute. And now it's just a matter of looking through each one and determining which one it looks like. I mean, it's going to be kind of hard because they might have a different scale. And also, I only see 3. Okay, so there's only 3. So out of the 3, I kind of like C, but notice that this scale is it starts kind of very low. Yeah, but C actually looks pretty good there. And then determine the linear correlation coefficient, which is the R, and that can be done in there. This problem seems like it's from another section, honestly. All right, let's move on. All right, so what we'll do is take a look at some of the problems from 6.2. So it looks like we're dealing with, let's see, we're dealing with 16 questions. And this is the section where we're dealing with a binomial probability experiment. Okay, I believe we call those the trials. It's the number of trials there. We will call the 2 mutually exclusive outcomes, success and failures there. A binomial probability experiment is conducted with the given parameters. Compute the probability of X successes in the N independent trials. And this is just geared for the calculator, so I'm going to demonstrate how you would actually solve this. You're going to go over to second distribute. You're going to go all the way down to binomial PDF. And then we're going to enter in the data. There's 30 trials. The probability is 0.98. And the X is 28. And I got 0.0988. 0.0988. We rounded it, to 4 places and we got the answer. All right, what if we were dealing with the values x equal to 4 and lower? Okay, so for this type of problem, we're going to use binomial CDF. We really have a choice. We can do the binomial exact amount from 0, 1, 2, 3, 4, and add them all up, or we could just use the binomial CDF. And so we got 11.25 and 4. And that means we're going from 4 and lower. And so I'm getting 0.8854. Right, they want us to calculate the probability of each one, exactly 0, exactly 1, exactly 2, exactly 3, exactly 4, exactly 5, exactly 6. And then we will get that full binomial distribution table. And then we can answer all kinds of questions from this. So you would do each one. N is 6, and the probability of a success is 0.75. Okay, let's see. Most of these questions, they seem pretty straightforward. You do have to dig into a few of them, understand certain. So if we set the probability of success as 0.2, and we set the slider of n as 10, what is the shape? And it looks right skewed actually. Set the slider, now increase p to 0.5. That looks normally symmetrical, so very bell-shaped there. Now what if we were to increase it to 0.8? Alright, so we're going to go all the way to 0.8. Left skewed. That left tail is extended a little longer this time. Skewed left. Alright. And we're going to wrap it up here. I'll let you finish the rest of this. But again, as always, let me know if you have any questions, and I will answer them. Take care.